Welcome to How to Succeed in ECE Without Really Trying. I'm Dr. Linda DeBrenner, and in this video we're going to talk about transients in simple RL and RC circuits.
So the first thing I want you to know is that transients do matter. In almost all digital circuits, certainly the interesting ones, the circuits are going to be switched on a clock that goes up and down and up and down in terms of voltages. And so this clock is used to time the circuit. Combinational circuits don't have a clock, but those are very limited in their value and use. In power systems, we also have relays that protect the power systems, and that involves the switching of the circuits on and off in response to changing supply and load demands. So transients matter both in the digital world and in power systems. Remember, when we first started talking about inductors and capacitors, we remembered from physics that V of t is equal to L di dt for an inductor. And for a capacitor, the current I of t is equal to the capacitance times dV dt. Let's consider a simple RC circuit. So what we're going to do is use loop analysis or mesh analysis to write an equation for this circuit. The difference between this circuit and the ones we've looked at previously is the inclusion of a switch. I'll talk more about that later, but the process is going to be the same. So for KVL, we'll just go around the circle here and write equations. Now, when we were talking about information circuits, we were assuming a steady state. This time, we're going to have to include the transient effects. So we're going to model our switch using a unit step signal. And all this is an equation that describes how the switch behaves. So we will assume that the time that the switch is turned on is called 0, and before the switch circuit's turned on, before 0, the output of that switch is 0, or the effect of that switch is 0. And for time greater than or equal to 0, the switch is going to be on. So this is just a simple model for the switch. It allows us to use mathematics to consider what's going on in the circuit. Notice that the derivative of u of t is going to be undefined at the point where t is equal to 0. To understand this fully, you have to have a basis in real analysis, but in electrical and computer engineering, what we're going to do is use the Dirac function. And this is also sometimes called the delta function. And this is named after Paul Dirac, who finished his career at Florida State University. And the Dirac or delta function can be defined as du of t dt, that's what it is, and we define it to be 0 anytime except at 0, and it's going to be undefined at time 0. And this is going to allow us to mathematically, again, model what's going on. So the Dirac signal is not a function, strictly speaking, but we could call it a generalized function. As far as we're concerned in this class, we can use it without worrying about all the mathematical details. So going back to our circuit, we can use Kirchhoff's voltage law and our understanding of the current voltage relationship for a resistor and for a capacitor. So we can write an equation for t greater than or equal to 0, minus v of t plus the voltage across the capacitor is going to be 1 over c, the integral from minus infinity to time t of I of tau d tau, and then the voltage across the resistor is going to be I of t times R, and that will all be equal to 0 based on KVL. So in each of these cases, we're just summing up the voltages over the elements just like we did before, but now we have to actually consider the transient response of that capacitor. The current across the capacitor is going to be 0 before the switch is thrown. And so that means for t is less than 0. So we can actually change our integral to go from 0 to t and include all the initial voltage in a constant. We will almost always assume that Vc of 0 is equal to 0, and we don't have to worry about that. So for this class, we will not have to worry about that constant voltage. When we take the when we differentiate that integral equation once, we get 1 over c I of t plus di of t dt times r is equal to dv of t. So we can also, this will become our working equation. We could also do the same thing using KCL and write the equation at the node whose voltage is the output voltage V out of t, and we can get the sum of currents in the same way. It's just a little more intuitive to do using KVL. Now that we have the equation, we can solve it. This is again solving differential equations. So we can solve the homogeneous part first, and we assume the function will be of the form ke to the at, and so di dt will be equal to ak times e to the at, just using plain old calculus. And so we get 1 over c times k e a of t plus r a k e to the at, and we can actually solve, and we'll get that k times 1 plus rc times a is equal to 0. The trivial solution where k is 0 is not useful, so we will require that a, which is in the form here, will be equal to minus 1 over RC. And we call this the first order time constant of the switch circuit, or of the circuit. Notice that this time constant only depends on the circuit and the components in that circuit, and it will impact the transient responses of the circuit. So we found the homogeneous solution. Now we must find the particular solution. So we need to define the input voltage, or the forcing function, which we'll call V of t. So we will switch the DC power supplies on and off so that we only need to set V of t to a constant voltage. So without loss of generality, we can assume that V of t is equal to 12. So we have a 12-volt source that's turned off or turned on. And so then the particular solution will default to the homogeneous solution, and we are done. That's just because we're assuming a constant V of t. And for time less than 0, we will end up with I of t is equal to 0. Now, we have obviously ignored the very specific current at time 0, and we can look at that and realize that we're using Riemannian integration, which is what you were probably taught in your calculus class. The area under a point in a function is going to be 0, so that value is going to be essentially indeterminate, and we can just use a physical interpretation of the problem and say that we will assume that we will have a value that can be determined. This is a circuit and it can be observed, and so we could, from the physical circuit, know what happens. So let's consider some specific component values. We'll start off with R is equal to 1 k ohm and C is equal to 1 microfarad. Then the time constant tau will be equal to 1 millisecond, 0.001 seconds. We can graph the input and the output. The input is going to be 12 volts, so that's the black line. And then the output across that resistor R will be a line or a curve that actually drops from 12 volts down to about 0. This is consistent with the idea that at DC, a capacitor acts like an open. One thing to notice is that the time equal to tau, these are milliseconds on the bottom, so around 1 millisecond, I marked it here, you can see that the resulting voltage across that resistor is about 63% of its total change. So it's going to be about 4.4 volts. Now let's look at our equations again. So if we write the KVL equation after the circuit is flipped and we're in steady state, we end up with the equation we had when we were doing information circuits, minus V plus I times 1 over SC plus IR is equal to 0. We can manipulate that to find that the I over V equation, I over V is going to be SC over 1 plus SCR. And we notice that the initial voltage for V is, I'm sorry, we know that V out is going to be R times I. So we can multiply both sides by R to find the V out over V is equal to SRC over SRC plus 1. We have done this equation analysis previously. Now let's look at this function to look at the denominator, SRC plus 1. We call this the characteristic equation. Notice that this characteristic equation does not depend on the input source. It is a characteristic of only the circuit and those component values. We can also look at the characteristic equation and find the roots of that polynomial. Those will be the poles of the transfer function. In this particular case, we have one pole at S is equal to minus 1 over RC. Notice this is the same as the time constant relation. Also, remember that our homogeneous solution to the circuit equation gave us the time constant in our earlier analysis. That means that the forcing function v of t does not impact the time constant solution at all, and our assumption that it was 12 volts doesn't change the time constant solution. Now let's consider a simple RL circuit. Again, we have now analyzed these circuits, or circuits very similar to this one. So we've now got an inductor and a resistor in series with a source. That source is called V of t. So just like before, we can write the KVL equation for t greater than or equal to 0. We get minus V of t plus L di dt plus I R equals 0. If we look at VO of t as being R times I of t, then we can write that KVL equation and rearrange it to get L over R times dV out dt plus V out of t is equal to V of t. So now let's consider the initial values. The current I of t is going to be 0 before we throw that switch, before the switch is closed. The inductor will initially inhibit the current, so I of 0 is equal to 0. That will be the initial value of the current after the switch is closed. This is going to be the same, of course, right before the switch was thrown. So often we will say that the voltage across a capacitor can't change instantaneously. And we'll say also that the current through an inductor cannot change instantaneously. These are aphorisms that we can use to kind of remind ourselves of what's going on. Going back to our differential equations, we follow the same process we did before. We assume I of t is equal to k e to the at. Then just like before, we can take the derivative of I of t dt and we get a k e of at, e to the at. So, writing our equation, L times a k e to the at plus R times k e to the at is equal to 0. So we can solve and get k times L times a plus R is equal to 0. Again, we dismiss the trivial solution where k is equal to 0, and we solve for the coefficient, the exponent value a, and a will be equal to minus R over L. This will be the first order time constant of the switch circuit. We also call this the RL time constant. So for now, we know that I of t is equal to k e to the minus RL of t for t positive. And we can also write V out of t is equal to k prime, which we don't know, times e to the minus R over L times t. So V out of t will be equal to R times I of t, of course. And so I of t is k e to the minus R over L times t. So that gives us V out of t is equal to R times k e to the minus R over L times t. Now, all we have to do is find out what k is. This time, we do have to consider the particular solution. In the RC case, it was much easier, but we can still do this. We will still assume a constant input of the form of a constant input, and we'll just choose 12 volts kind of randomly, okay? And then we'll deal with it later. The particular solution will be in the form of V of t, and we will assume that that's a constant voltage. We can call that's a reasonable assumption to make, and we'll call that the steady state voltage, VSS. Then from our differential equation, we know that L over R times the derivative of VSS of t dt plus VSS of t is equal to 12, which is what our initial assumption was. We know that VSS of t is equal to VSS, and so dVSS of t dt is equal to 0, and that means that VSS must be equal to 12. Okay? And this will be true from t is equal to 0 to infinity, just above 0 to infinity. We need to still determine that constant value k prime. Okay, and so we know that v out of t is going to be equal to the VSS, 12, plus k prime e to the minus r over L times t. So v out of t is the sum of the particular solution plus the homogeneous solution. And so we know that I of 0 is equal to 0 because the conductor in the current in the conductor cannot change instantaneously. We also know that v out of 0 is equal to 0, just based on Ohm's law. From this, we get v out of 0 is equal to 0, we know, is equal to 12 plus k prime, and that tells us that k prime must be equal to minus 12. And so the final solution of that output voltage must be 12 minus 12 e to the minus r over L times t for t greater than or equal to 0, and it's 0 otherwise.
Thanks for watching. See you in the next video.